Okay, moving on to question 7. In 7, we are titrating aqueous ammonia with hydrochloric acid as titrant. So in setup, ammonia is in the conical flask and HCl is in the burette. We are supposed to monitor the pH change as the HCl is added into the conical flask. So for such a question, if you were to think through about a titration curve, you expect the titration curve to look something like this. Alright, it will be called the Z-shaped curve. pH will be high because you start off with ammonia, a base, and then you have a region of rapid pH change, and then after that, so if this is the equivalence point, what do you think the pH should be? Alright, so at the equivalence point, you will have NH4Cl, which NH4 plus Cl minus. NH4 plus is the conjugate acid of NH3. So if you think about it, this pH will be definitely it's a conjugate acid hydrolyzed to give, so NH4 plus, right? In water, it will hydrolyze to give NH3 plus H3O plus. So this H3O plus will cause pH to be less than 7. Okay, so let's take a look at the question. We have Kb of ammonia and calculate pH of ammonia solution. This is a simple question. Start off with ammonia itself. Ammonia is a weak base, so we can make use of the formula of OH minus equals square root C times Kb. So just sub in the values of the concentration of ammonia, 0.2 mole per dm cube, and then the Kb is given to you. Sub in these two values into the formula, you get your OH minus, find POH negative log OH minus, and then from there you can find your pH. Okay, so this one is quite straightforward, nothing much for me to highlight. Simple calculation. We move on to B. For B, you're supposed to look at equivalence volume of the acid required for neutralization of 10 cm cube of aqueous ammonia. Okay, so if you take a look at the question did mention state, which means it's unlikely you need to do calculation. And another interesting thing you see in this question context is that HCl and aqueous ammonia both have the same concentration. So this will give you a clue in terms of the equivalence volume. Alright, so from this, since the mole ratio is 1:1, alright, and the two solutions have the same concentration, the equivalence volume will be the same volume of HCl to reacting the same volume of NH3 because they have the same concentration. Okay, so that's part B. In this case, you can see I did not do any calculation, I just simply state. Okay, to calculate the concentration of a salt form at equivalence point. Okay, so if this is the neutralization equation, we know that at equivalence point, the mole ratio of your NH3HCl and NH4Cl will be 1:1:1. The number of moles of NH4Cl is the number of moles of HCl present. Okay, so number of moles of HCl used against equivalence point is 10 cm cube as calculated in B. So this is from B, right, at 10 cm cube. Multiplied by the concentration of HCl. So volume of HCl multiplied by concentration of HCl. This will give you a number of moles of HCl, which is the same as the number of moles of NH4Cl. Right, number of moles of HCl, which is the same as number of moles of NH4Cl. What the question wants is the concentration. So concentration, after you get number of moles, we need to divide by the volume. So in this case, many of you will be very tempted to divide by 10, but if you take a look at the setup, alright, so I originally have 10.0 cm cube of ammonia. Now at equivalence point, I've added in 10.0 cm cube of HCl. This is at equivalence point. So the total volume will be 10 plus 10, which is therefore equals to 20 cm cube. And therefore, to find the concentration, you need to make use of the moles. You divide by the volume. Alright, so moles divided by volume, 20 cm cube. You need to convert it to dm cube. And therefore, you get 0.100 mole per dm cube. Okay, that's answer for C. Okay, moving on for D. Okay, we are supposed to sketch the graph to show the variation of pH with the volume of HCl added. And there's a number of information given to you. 1, the pH at equivalence point is approximately 5.1, and this we've discussed earlier on. Why is the pH 5.1? So if you think about it, at equivalence point, you only have the salt. The salt for this titration is your NH4 plus Cl minus. So NH4 plus is the conjugate acid. So when you have NH4 plus in solution, in the presence of water, it's going to donate a proton because it's functioning as a weak acid. You have NH3 plus H2O, H3. Okay, let me just write this properly. H3O plus. So this H3O plus generated will cause pH to be less than 7. Okay, so after adding 20 cm cube, so this is beyond equivalence point already, because equivalence point was at 10 cm cube, right? Your pH will be 1.2, and this is expected, right? Because as you add in more acid, the pH of the solution will decrease. Okay, so we are going to make use of our results in A and B to sketch a graph. Okay, so what do we know? The initial pH, it's 11.25. That's calculated for part A. Alright, that's the pH of the NH3 solution. Okay, that's point number 1. Let's call this point number 1. Point number 2 is given in the question. Equivalence point of pH is 2, and this is also the region of the rapid pH change. The equivalence volume will be 10 cm cube. Again, it's from B. Again, this 2 forms my point number 2. And then pH after adding 20 cm cube of HCl is 1.2. Then that's given in the question over here. Okay, that's our point number 3. So in this case, we have 3 points to indicate on the graph. So having a pH against volume of HCl, the 2 specific volumes of HCl we're looking at are 10 cm cube and 20 cm cube. So let's have 0, 10, and 20. So the first pH at 0, it's at 11.25. So 11.25. Okay, the next pH at equivalence point is 5.1. So 5.1. Okay, 5.1. The initial pH, it's part A, right? 11.25. And then after adding in 20 cm cube, that's 1.2. Okay, so you have 3 points here. 11.25 at 0 cm cube initial. 5.1 is at 10 cm cube. And then 1.2 is at 20 cm cube. So let's draw in the construction lines first. How then do we get the correct shape of the graph? Okay, so you must remember the equivalence point. Alright, the equivalence point is a region of rapid pH change. So the graph gradient here should be steep. Okay, so you can see, and this is generally the midpoint of the rapid pH change value. Okay, so this is what you expect. Start from 11.25, drop, gentle drop, in effect rapid pH change, and then drops to 1.2. So that's how you can get the shape of the graph. Okay, so I'm going to make use of this graph to consolidate your understanding of titration curve again. So let's call this point number 1 your initial pH. This one, let's call it point number 2 your equivalence point. Okay, point number 3 before equivalence point, and point number 4 after equivalence point. Okay, you can pause this video now and start to annotate what are the key species, the identity of the species at these 4 points. Alright, before you check your answers. Okay, so you can pause this video now. Okay, take some time to scribble down the identities of the species at these 4 points, and therefore give you a clue of what formula you can use to calculate the pH. Okay, so let's take a look at your answers. Initial pH, you only have your ammonia present. Recall your setup, it's your HCl in the burette. Conical flask, it's your ammonia. Okay, so you only have ammonia present. At equivalence point, you have only your salt, NH4 plus Cl minus. This is the salt containing the conjugate acid. Okay. Then before equivalence point, so if you think about before equivalence point, what do you have? You add in some HCl already. You have some ammonia remaining. plus, because ammonia is not fully neutralized yet, and some NH4 plus that's formed from the neutralization, right? Because HCl and NH2 will react. So you have some ammonia remaining and some NH4 plus form before equivalence point, and therefore this region here, it's a buffer region. Okay, and after equivalence point, okay, now that you have added in more until all the ammonia is gone, you now just have excess HCl. So quick run through of the equations that you can use for, we're going to use black to annotate the formulas. For point number 1, the formula you use, because it's a weak base, our formula to use will be OH minus equals to square root C times Kb. Okay. For point number 2, because it contains a conjugate acid, alright, and NH4 plus will dissociate to form H2O plus, right? Plus H2O, you'll dissociate like a weak acid. It's like a weak acid to form H3O plus NH3. We can view this as an acid, weak acid solution. So H plus, it will be equal to square root C times Ka. What's the C? To be more specific, will be square root NH4 plus, then times Kw over Kb of NH3. Alright, this is how we find a H plus concentration. For the buffering region, because this is a basic buffer, you make use of the formula POH equals to PKB plus log your ammonium, which is a salt, over your base NH3. Okay, and then after equivalence point, you basically find excess HCl, the amount, then you find HCl excess, and then you can find H plus, and then therefore you can find your pH. Okay, so that's what we're going to do in the next part of the question. Okay, in part 2, we're supposed to show by calculation. So again, these are the species present. Okay, you can pause this video now to see if you have gotten all the species correct. Okay, again, knowing the species at each different part of the titration curve will guide you to get the different formulas correctly. Okay, so important for you to exercise this thought process. You must know what's the approach to get the formula. So in the event if the question asks you to calculate a pH, you know what formula to apply. Okay, so you can go through the same process, alright, just have a schematic to help you visualize, alright, is it before equivalence point, what do I have in a conical flask? Okay, if not, I'll record the next video of part 2, E and F in another video.